This lesson is on reversible reactions and equilibrium and the calculation of equilibrium constants. Reversible reactions are reactions which convert reactants into products and products into reactants at the same time. In other words, the reaction goes both ways, and if it goes both ways at the same rate, it is going to be at what we call chemical equilibrium, a type of dynamic equilibrium which there's no net change. The reactants change to the products, but because the products change back into reactants at the same rate, the amount of reactants and products remain constant. I will show you tomorrow a demonstration involving the blue bottle. I will also show you a demonstration involving this reaction. But here we have a substance that can be yellow, so the reactant side is yellow, the product side is blue. If the reactants are the predominant species present, then the system will look yellow. If the products are the predominant species present, then it will look blue. If it's half and half, we'll look green, green being the combination of blue and yellow. So we can say the equilibrium position is to the left when it's yellow, the equilibrium position is to the right when it's blue, it's in the center when it is green. So one of the things we'll talk a lot about is equilibrium position. Where is this equilibrium reaction? Is it more towards the reactant side? Is it more towards the product side? Or is it directly in the middle? All that being described as equilibrium position. If we have a reversible reaction and we start with nothing but reactants, so say we have only the SO2 and the O2 present, that means there is 0 of the SO3. Only the forward reaction then would be possible. If you only have reactants, no products, the reaction then can only go in the forward direction. But think about what's going to happen over time. As the SO2 reacts with the O2, their concentrations are going to decrease, so we can see them decreasing over time. And as the product forms, its concentration is going to increase over time, so we can see the concentration of the SO3 increasing over time. As the concentrations of our reactants decrease, then they are going to slow the forward reaction down because there's fewer of the reactants to collide with each other. As the product increases, the reverse reaction is going to increase in rate because there's more and more of the product to collide with itself to go backwards. Eventually, the forward rate and the reverse rate become equal. At that point, we have reached what we call equilibrium, and there's no net change over time. If we were to do the same thing with nothing but the products, then the exact opposite would happen. If we started nothing with but the product, then there'd be 0 reactants and only the reverse reaction would be possible. But again, over time, as the products changed into the reactants, their concentration would decrease. The concentration of the reactants would increase. So again, here we see product decreasing, reactants increasing over time. And eventually, again, the reverse rate is going to equal the forward rate. The reverse rate is going to slow as the concentration of the products decreases. The concentration of the reactants is going to increase, and the forward rate is going to increase. When the two become equal, again, we have reached chemical equilibrium, and there's no net change in the amount of reactants and products possible. This can all be quantified mathematically in what is called the equilibrium constant, called KEQ. We will typically just call it K. And the expression, the mathematical expression for K comes from the law of mass action. Basically, it means you can write it directly from the balanced chemical reaction. So here we have a chemical balanced reaction in equilibrium. Note the double arrow indicating that it is going both directions, and we're assuming it's at equilibrium. The forward rate equals reverse rate. So note it's always products over reactants. The molar concentration of C times the molar concentration of D raised to their coefficients divided by the molar concentration of A times the molar concentration of B raised to their coefficients. And so if you know the balanced chemical equation, you can directly write the from the law of mass action, and you can get the expression for the equilibrium constant from that. If the value of KEQ is greater than 1, that is, you have more products and less reactants, then the equilibrium position is to the right. There are more products than reactants. If KEQ is less than 1, then there's more reactants, less products. So the denominator is the larger number, the numerator the smaller number. And if KQ is equal to 1, then you have relatively equal amounts of reactants and products, and we say the equilibrium position is in the center. We will typically ignore the units for K, and so don't worry about units for the equilibrium constant. Okay, let's say I've got this system in equilibrium. If I wanted to write the expression for KEQ for this one, again, it's going to come from the law of mass action. So it's always products over reactants. So it's going to be the molar concentration of the sulfur trioxide squared, because we have 2 moles of that, over the molar concentration of the SO2 squared, because we have 2 moles of that, times the molar concentration of the O2. And so that is the written expression for KEQ for that one. If I actually give you numbers, then you can actually solve for the value of K. So here we have a system in equilibrium given by the balanced chemical equation in the middle. And we're going to let the COCl equal a 1.25 molar concentration, the carbon monoxide equal a 0.262 molar concentration, and the chloride equal a 0.156 concentration. So now we've got numbers to plug in. Again, we can write the law of mass action. KEQ is going to equal the products over reactants. So we have this times this. The the exponents are going to be 1 in each of these cases, because there's just one of these and one of these over the reactant. Again, we have just 1 mole of the reactant, and we're simply going to plug those numbers in and solve. So this is going to be 0.262 molar. This is going to be 0.156 molar, and the products, reactants, are going to be the 0.125 molar. So we've just taken those numbers, plugged them in, and the value comes out to 0.327 molar, or 0.327 moles per liter. But it's just plugging numbers in and solving. Okay, one more sample problem here with just the calculation of K. What is the value of K given the following data? So here's our equilibrium expression. Again, it's always products over reactants. So it's going to be the SO2 squared times the O2 over the SO3 squared, which will look like this. And we're going to let the SO3 equal 0.043. The SO2 equal 0.13, and the oxygen equal 0.11. So we'll just plug them into their respective positions. And so the SO2 must be squared times the 0.11 for the oxygen over 0.43 squared. And that gives us a value of 0.010. Again, we'll ignore units for K. So pretty simple process. One more sample problem. What if I gave you the same reaction at the same conditions, so the value of K then is going to be the same. Again, it's a constant, an equilibrium constant, and ask you what is the concentration of oxygen when given the values of the SO3 and the SO2. Pretty much the same problem. K we now know is 0.010. We have the value of the SO2, the value of the SO3, so we need to solve for the value of the oxygen. So that is going to be our value of X, and it's just doing the math and solving to get the value of the oxygen at the equilibrium constant. And that is it. Thank you.